Hello. We will be working through question 54 and 55. And the answers to these questions are D as in dog and B as in boy. So let's select those. Now this one's kind of easy if you know the right answer, but most of you don't know the right answer. So we're going to have to do a test for independence. And we haven't done one of those in a while, so let's do it. I look at this table and I decide, is there some type of an association? So all an association means is that the two items are not independent. So let's write that down. Association. The two events are not independent. Let's write that down in our notes. So an association means the two items are not independent. So, well, what does independent mean? That means that the occurrence of one event does not change the other. So whether or not you have a job, let's say the probability of everybody in Bogey having a job is a third of everybody in Bogey has a job. So whether you're a junior or a senior, doesn't matter because a third of everybody has a job. But if a third of the seniors have a job, but a third of the, if a different percentage of juniors have a job, then there is some type of association, meaning the two are not independent. So if I know you're a junior, I'm more or less likely to be able to predict whether you have a job. And that's what that's what probabilities has to do with statistics and inference. So let's do it. The best way to calculate, and I'm getting this out of page 327. So you want to pause the video and turn to page 327. The formula says the probability of A given B must be equal to the probability of A if and only if they are independent. Additionally, if and only if they're independent, the probability of B given A would also need to equal the probability of B. So using the words of the problem, the probability of a job given you're a junior equals the probability of a job. So if a third of the juniors have jobs and the third of everybody has a job, that's what we would call independent. Independent of whether or not you're a junior, a third of people have jobs. We could also do it flip-flop the other way. So that's what this says here. So I can do a test for independence. And so I'm already, though, looking in the table. Does it look like a lot more juniors and seniors have jobs? So does knowing whether or not someone's a junior or senior tell me whether or not they'd have a job? So I'm going to zoom in here on the table, and it seems like the people that have a job, 13 out of 18 juniors have a job, and 13 out of 39 seniors have a job. So there's actually the same amount of people with jobs, but there's way more seniors. So actually, that does look like there is some type of an association because that ratio is different. So taking a look at this, I'm already focusing in on whether or not it looks like there is an association. Knowing one does help me predict the other. So let's read my choices. It says, since more seniors than juniors are in the survey. Well, we know that does not matter. I can have more juniors or more ladies or more men in my survey. It doesn't matter as long as I have enough men and enough women, and enough juniors and enough seniors. And that's why we calculate the percentage. I'm trying to compare what percent of juniors have jobs, what percent of juniors have jobs. And that's what D says. Since the proportion of juniors having jobs is larger than the proportion of seniors having jobs, then that's why there is an association. So I'm going to pick D. Now let's look at the math. So again, this formula, I can actually calculate it. So using that formula, I can go ahead and calculate what's the probability of having a job given you're a junior. And is that equal to the probability of having a job? So as stated previously, if everybody has a job or a third of people have a job, this should also be a third. So the probability of having a job, given that you're a junior, well, given that you're a junior, so we're only going to talk about this one column here, given that you're a junior, so that's really only 18. So given that you're a junior, 13 of those have jobs. Now the probability of having a job is 26 students out of 57 have jobs. So to do the math, we just cross multiply and see if the two equal each other. So 13 times 57, 18 times 26. Decide if the two cross products equal each other. If they do, that's independent. So when I multiply those, I get 741, and that's not equal to 468. So I already have evidence that I was probably on the right track, and there probably is an association, because if these were equal, it'd be independent. And again, independent means that there is not an association. So because this is not independent, that means there must be an association. I can keep going and I could calculate the other way around. What would be the probability of juniors given jobs and the probability of a junior? So the probability of a junior given you have a job, if that was equal to the probability of just being a plain old junior, that would tell us they're independent. Now we kind of already know they're not. So given that you have a job, so looking only at this column, given that you have a job, that's 26 people, and then juniors. So there's 13 out of 26 that are having jobs. And what's the probability of a junior? Well, there's 18 juniors out of 57. So once again, notice I get similar fractions, and when I cross multiply, I get the exact same numbers. And so that's why it's interesting when we cross multiply, we realize that, like, wait a minute, I'm multiplying exactly the same two numbers, so I'm going to get the same outcome here. And again, very certain that this is not independent, which means there must be an association. I could also have done this with seniors, so I just did on another piece of paper. If you accidentally did seniors, the same exact thing could have happened. I could have calculated the probability of job giving a senior and then the probability of a job, and vice versa. Once again, these cross products are not equal. Question 55. This one I think was a pretty easy one. We look at this question, and if you didn't get B, let's talk this through. The formula for standard deviation, if you're estimating it, this is not the real formula, but if you're having to estimate it off of a graph, the standard deviation is max minus min divided by 3 if it's normal or approximately normal. So the max looks to be around 80, minus 20 divided by 3, and I get 20. And that was my choice. Again, let's just use a few more minutes to review. One standard deviation would be plus or minus 20. Or what am I saying? 10. Sorry. I had just like a problem there, right? Because I got 10. That makes sense. 20 is the width of the full one standard deviation plus or minus 10. So the width of that is 20. So that would tell me not the standard deviation, but the width of one standard deviation is 20, the width of two standard deviations, or the width of 3 standard deviations, because the full range. So the formula, technically, I should change this, would be 6. So in a way, there's 6 equal increments, 3 on the left, 3 on the right. So the formula would be, to find this standard deviation, I'd need to divide max minus min divided by 6, and that would give me 10. That makes me feel better. And again, 20 was correct, but it would be 10 to the left, 10 to the right. So the standard deviation of 10 matches my picture. Thanks for joining.